Hello, my name is Andy Hammermeister and I'm the Director of the Organic Agriculture Centre of Canada at Dalhousie University. This is part 2 of a 3-part series on experiencing your soil for farming success. In this session, we will talk about land capability for agriculture and how we might manage the basic soil physical and chemical properties that we have in our soils. So if we go back to this kind of introductory slide that I've been showing, you can see that we need to consider basic soil characteristics, how we manage them to ultimately influence how the soil functions and how healthy it is. And that soil health and function will ultimately influence the crops and their services and how productive they are, and perhaps how we might contribute to other ecosystem services such as carbon sequestration and water cycling and habitat provision and so on. And ultimately that will lead to greater sustainability. So today we're going to start by talking about soil capability. And this is a term used to express the ability of land to support a particular type of use without causing permanent damage. Now, when we think about land capability, we need to consider the basic soil properties that we are starting with. I introduced those soil properties in my previous video on the origin of soils. So today we're focusing a little bit more on land management practices and how they might alter those basic soil properties. Ultimately, however, those basic soil characteristics are when describing land capability, the natural soil characteristics were used to identify their potential for productivity in agriculture. So there has been historically a mapping exercise that took all of the natural soils and identified their basic capability for agricultural production across the country. And you can see this map that indicates where the agricultural regions of the country might be. When we think about basic soil properties, we need to think about their fundamental characteristics. And a soil basically is made up of organic material, so that's the dead and decomposing materials of plants and animals and insects and so on that have lived in the soil. Mineral matter, then we have water and air. And you can see that water and air, their proportions will change dramatically depending upon the management conditions and the environment that the soil occurs in. But it's really important to understand that water and air are a very big part of the soil volume, and that can have a big influence on the productivity of the soils themselves. The mineral matter will also influence things like soil pH as well as nutrient availability and cation exchange capacity. So let's take a look at the land capability for the Atlantic region. And again, this is based largely on the capability of the natural soils. And so when you look across the region, you can see that most of the region is pink. So what does that mean? If you look on the top right of this slide, you can see that there's 7 classes of soil. Class 1 is the best agricultural land that has no limitations to its productivity. Class 7 has virtually no capability for agricultural use or even for permanent pasture. So if you look at the list of potential limitations down below, they range from climate and soil structure, erosion potential, fertility conditions, periodic flooding, moisture in terms of water holding capacity or saturated conditions. So excess water would be an issue, salinity, stoniness, depth to bedrock, so very shallow soils, and you might even just have steep slopes, so the topography is not suitable for agriculture. So when you look across the map and you think about the natural soils that occurred in our region, and perhaps lack of soil in some cases because of shallow depth to bedrock, you can see that much of our region occurs in Class 7 land, the pink color. Now we can, and then there's our other areas that are reaching up to Class 4 and potentially even Class 3 land. And even we might have a few patches of Class 2 land in our region. So it really varies depending upon where you are and what kind of mineral deposits you have from the parent material that was left behind from the last glaciation, and also how deep the soils are to bedrock and perhaps drainage. Of course, these soil characteristics, many of them, or at least some of them, can be altered and change the capability of the soil. And so we'll talk a little bit more about that. So when we take a natural soil, which you might see on the left, which is a podzolic soil forming under a more acidic and a little bit sandier soil condition, you have that bleached AE horizon that's essentially acid washed, and it's moved iron and maybe a little bit of clay down into the B horizon. And when we take that soil such as that from a natural condition and convert it to agricultural land through our management practices, the first thing that happens is that we're disturbing the topsoil. So we're mixing that the organic layer at the soil surface with the AE horizon or whatever material there might be there. And that all gets mixed together. And you can see that illustrated on the right-hand side of the screen. Then, of course, over time, by applying different management practices, we can alter the characteristics, especially of the topsoil. So by growing different kinds of crops, we can enhance organic matter buildup in the surface of the soil. We can adjust the soil pH, which we'll talk about a little bit later, which will influence nutrient availability and so on. So let's talk a little bit about some of the practices that we can use in our land management to improve our soil properties. And that can range from drainage and shaping, liming, tillage and subsoiling, stone removal, crop rotation, organic amendments, residue management, cover crops, pest management, and equipment passes. So we won't talk, and there could be more practices than this. We won't go into all of these in detail. But the bottom line here is that by taking our basic soil characteristics and applying management practices, we can alter the soil health and function and influence ultimately the services that the crops provide us. So let's take a look at a shallow undisturbed forest soil and take a look at an example of where we might start from. And I'm going to give you a few examples here of different soil conditions that you might begin with. So here's your shallow undisturbed forest soil. And so there's a fair bit of accumulation of organic matter at the surface. This is leaf litter and root material. There's a acidic or acid washed little bleached AE horizon here. And then this is a fairly shallow soil. It's not very well developed, and you have a weak B horizon. And it'd be a podzolic soil, most likely. Perhaps moving into a brunisolic soil condition. So if we take that land and if we have a forested soil such as this and we clear it, we'll go through this process of removing all of the forest vegetation. So perhaps shredding the trees and then de-stumping it and using deep root rakes that will actually remove all of the roots and whatnot. And in doing so, you can see that a lot of the organic matter is being removed. In this case, in the process of pulling all the roots and stumps up to expose the mineral soil, this whole layer of leaf and fibric and humic material is being pulled up and piled up in the windrows for gradual decomposition and perhaps even burning. And it may or may not be returned back to the soil. And you can see there's a lot of organic matter that's brought into that windrow area. And that has all been removed from the mineral soil surface. So what's left behind might be a few remaining roots and stumps, but you have a disturbed soil condition where that soil profile has been mixed up, and you could have varying degrees of organic matter removal and depths of disturbance that have happened. You might also have poorly drained conditions in some of these soils, and that's something to watch out for. So once you've cleared the land, and this is actually, the previous pictures were from Newfoundland, but once you've cleared the land, you might end up with a landscape such as this. Again, another example of a soil profile where the topsoil has been kind of mixed up, and you can see remnants of the AE horizon. There's even some charcoal left behind here from when perhaps some of the organic material was burned. So when you're starting with a soil like this, you are likely starting with relatively low soil organic matter, probably low for soil fertility in our region, likely acidic conditions, perhaps poor drainage. You might have slope issues, stones, there might still be wood in the soil, and depending upon how long it's kind of sitting, you might have some perennial weeds or other vegetation, native perennial vegetation that might be trying to regrow in this disturbed site. Another example would be a pasture site, and this is actually a photo out of BC, but essentially when you have a pasture, a piece of land that's originating from pasture, it could have been in that condition for quite a while, so it may have pretty good soil organic matter. It really depends on the grazing regime that was applied on the pasture. If you have really intensive grazing, you could have fairly shallow, very little organic matter deposition. You could have lots of soil compaction, and you could have problems. In a well-managed pasture system, you could have really good soil organic matter buildup and nutrient cycling. And depending upon where you are and how the pasture has been managed, the soil pH could be relatively low in our region. And you might have poor drainage conditions. A lot of the pasture soils are lands that are have relatively low agricultural capability in the first place, otherwise they would have been cultivated. But some of the cultivated areas or good land has been brought into pasture just because of the nature of the farm. Another example is recent hayfields, and this photo is from BC, but we can see many areas of in our region within the Atlantic region and the Maritimes especially, lots of land where that might be sitting vacant, that might be getting cut for hay. Those soils might be depleted of nutrients if nothing has gone back into them. They also, if it's a very actively managed hayfield, then it could have good soil fertility and good pH, perhaps even have good drainage condition. But if it's land that's been sitting idle for a long time and it's just basically being harvested for hay with no inputs returning, then you could have poor drainage and poor soil pH conditions as well. And perhaps some issues with perennial weeds that are developing in these soils. So it really varies depending upon the history of the hayfield and how intensively it was managed. And then we can get into land such as this, which is cultivated cropland. And so if you get into cornfields, for example, and corn soy rotation fields, you could have higher background soil fertility levels depending upon the management regime. The soil pH is likely to be fairly good. A lot of annual crop farmers will manage the pH pretty well. These soils either might be naturally well drained or money has been invested into drainage. So you're likely starting from a better soil condition in most cases on these cultivated soils, unless the soil has been degraded and due to erosion and nutrient depletion. So again, you can look at the soil and look at the organic matter content and get a sense of what its background history is and its fertility status. So we kind of hinted at soil degradation, and if you have cultivated lands that are undergoing frequent disturbance events and you have bare ground, and you could have issues of organic matter loss, vulnerability to soil erosion, repeated vehicle or traffic on the fields could cause severe compaction issues. Livestock can do this as well. You could have salinization issues. This is a more common issue in the prairies. And you can have contaminants such as heavy metals, pesticides, and other toxins in the soil. This is a particular issue in parts of Asia where there's much more heavy metal contamination risk. Ultimately, you're running into a soil with poor background conditions of fertility, perhaps pathogens, poor rooting depth or conditions. They might be drought or flood prone. They might have crusting and weeds and perhaps even a toxic environment. So depending upon the history of the soil and how it's been managed, you could have severe degradation issues that you're dealing with. So that brings us to soil health, and this is become very popular to discuss in agriculture, and I'm really excited and happy about that because we're really focusing on many soil properties at once and the ultimately how well the soil is able to function and support our crop production and other ecosystem services. And certainly one of the leading organizations in the soil health movement, if we might put it that way, is Cornell University and their Cornell framework for soil health. And so I've just pulled up an example of a soil health sheet here, soil health assessment that illustrates some of the different properties or indicators of soil health that you might use. And those would include physical, biological, and chemical properties. So we're going to start in this presentation, we're going to talk about physical and chemical properties, and biological properties will be discussed in the next presentation. Now, having said that biological properties will be discussed in the next presentation, I think it's really important that we lay a good foundation, and we need to understand that having a good rooting environment means that we have to have healthy soil biology, and basically that depends on having a healthy soil condition. So if we're looking at diseases in the soil and poor rooting issues, those conditions are a result of having a vulnerable host, so the crop is vulnerable to the disease. You have to have the pathogen present, and then you also have to have an environment that's favorable to the disease. And so I'm going to be talking quite a bit about soil environment conditions and how we want to ensure that we have a good rooting environment to promote soil healthy crops. And there's a nice illustration from the Cornell guide that shows their root assessment, their biological assessment for root health. And you can see from A to D the transition from healthy roots to really poor rooting environments. And when we look at the properties of the soil that maintain that good rooting environment, you can see that soil structure, drainage, biological activity, and pH are really important. And we'll be focusing on not so much the biological activity, but some of those basic soil physical and chemical soil characteristics. So let's come back to some of this recently cleared forest site, and this is a shot from Newfoundland, and some of the soils are really shallow, or there's a lot of stones, and you can see a stone pile here in the background where the farmer has been trying to remove the stones from the fields and to make them more workable. Obviously, if you're trying to grow root crops, this would be a problematic soil condition to have. And it's kind of hard to avoid the stones, and you might deliberately consider what kind of crops you're growing and so that you're not having to deal with the stones in your harvesting operations especially. There has been a recent innovation though in stone management, and that has been a rock pulverization, or called an alternative name is called lithic mulching. And so essentially it looks like a great big rototiller on the back of a really big tractor. So you're talking really high horsepower here that is essentially pulverizing the stones. And so we had dug a pit here, and on the right hand side you can see soil that is natural after the trees have been cleared and the organic matter has been removed. You can see there's a lot of stones that have been dug out of the soil on the pile here. And on the left-hand side is soil after it has gone through the rock pulverization process. You can see that there's very few really large stones remaining. Now that doesn't mean that all of the stones have been converted into healthy soil mineral material. A lot of it would become kind of gravel-sized particles or maybe sandier-sized particles. But this process would alter alter the soil chemical properties and make some minerals and nutrients be released from the stones. Could affect soil pH. It all depends on what kinds of rock you're dealing with and how finely they break up. One other thing that you can see in the at kind of the bottom of the rototilling or the pulverization unit's depth, you can see that there's other stones remaining beneath that depth. And I do have some expectation that those stones will be brought to the soil surface over time as a result of frost heave and then perhaps equipment pulling it up as well. So a combination. So how do we bring this soil into production? Well, I'd start by looking at soil drainage conditions. Perhaps you'd look at consolidating the fine materials up into ridges to get better drainage and warmer soil conditions. Soil phosphorus deficiency is going to be a big issue, and obviously the organic matter has all been removed, so we have some fairly significant issues here. But the main the thing I wanted to illustrate here was the rock pulverizer, which is a very fairly costly and intensive, very soil disruptive approach to managing stones, but something that's happening out there. So after you've dealt with stones, either by removing them, learning to live with them, or pulverizing them, we look at other soil characteristics in terms of their particle size. And so here's an illustration of the different particle size classes within soil. And those would be sand, which could be up to 2 millimeters in size, so 0.05 to 2 millimeters. Then you have silt, which is quite a lot smaller, and then clay particles, which are really, really tiny and would be less than 0.002 millimeters in size. So very, very small particles. And these particles are really, particle size classes are really important because they influence both the physical and chemical properties of the soil. So let's take a look at what these particle size classes mean. So if you start with a sand size particle, say they have an average diameter of 1 millimeter, you'd have in the order of 400 grains of sand in 1 gram of soil and material. And if you measured the surface area of all of those particles, it would end up being about 22.5 square centimeters, so not really all that big. If you go to the opposite end of the spectrum where you look at the montmorillonitic clays, the clay particles are very, very tiny, and the number of particles that you have per gram are 4 times 10 to the power 14. So huge numbers of particles of clay in 1 gram. And that 1 gram of soil, if you measured all of the surface area of all of the particles, individual particles, it would be over 8 million square centimeters. So that would be roughly the size of an average house lot in terms of surface area per gram of soil. It's like mind-boggling. It's hard to imagine that. But it shows you the contrast in surface area. Now that's important when we talk about cation exchange capacity and also water holding capacity of the soil, which we'll get into a little bit later. When you take sand, silt, and clay and you mix them together, you end up with different soil texture classes. And in the middle, you have this thing called loam. So loam is not a particle size class. It rather is a soil texture class. And loam basically is a mix of various proportions of sand, silt, and clay together. And obviously, we're pretty familiar with loam soils and recognize them as something that's fairly beneficial properties, or is fairly easy to grow crops in and fairly desirable because you don't have extremely sandy or clay conditions. So what does that mean? So when I look at the different properties of sand, silt, and clay, there's a whole list of soil properties that are influenced by those particle size classes. And so let's look at a few of them just as an example. So sandy soils have a very low water holding capacity compared with clay soils. And if you have a loam soil that's a mix of sand, silt, and clay, you'd have a nice in-between condition. In terms of aeration, again, you have really good aeration with sandy soils. You could have poor aeration with a clay soil because the particles are so much closer together and the soil pores tend to be quite a lot smaller and there's more water being held in the soil. So with drainage, you could have very rapid drainage under sandy soils unless you're on some sort of impediment that's keeping the water up. And clay soils can be very slow in terms of their drainage. Down below we have leaching potential. So sandy soils are very vulnerable to leaching of nutrients, whereas clay soils are not. And sandy soils have a very low cation exchange capacity, whereas clay soils have high cation exchange capacity. So, and we'll talk about that a little bit more. But this just gives you an illustration of the wide range of soil conditions that are dependent upon soil particle size classes and ultimately the soil texture, the mix of sand, silt, and clay that you have that you're working with. So that's why pretty much all soil tests and soil health tests look at soil texture as one of the basic soil properties. When we think about soil texture, there's very little that we can do to change the soil texture. It's hard to bring sand. You can bring a little bit more sand into your soil, but if you have a really heavy clay soil, it's hard to bring enough sand in to actually dramatically change the texture, especially if you're dealing with a larger land area. If you're dealing with smaller garden beds or potting soils, then that's a whole different story, and you can adjust that fairly easily. So the easiest way to alter your soil properties is, in terms of texture, is to change the soil organic matter content. And whenever you improve your soil organic matter content, you're generally improving the properties under those extreme conditions. Okay, so let's take a look at soil structure. And this is a fairly classic, a little bit older photo of different soil structures, and you go from a nicely structured soil on the left that has nice little clumps that we call aggregates and even root distribution through the soil, to on the right we have a non-structured soil, and it's just this one big clump with no individual aggregates. In soil classification, we would classify the soils based on their size and shape and how strongly they are held together. And so granular soils are tending to be more common in topsoil and are a very desirable condition to have. Platy soils tend to have a layering effect, and those are more present in natural undisturbed soils. But you can also get that platy effect as a result of shearing from compaction and tillage, which we'll illustrate in a moment. Otherwise, the prismatic, angular blocky, and subangular blocky conditions are more typical in natural soils under undisturbed conditions. But if you start having these big blocks of soil, then it's harder to manage them for sure. So what factors influence soil properties? There's climatic conditions such as freezing and thawing, wetting and cooling processes can be a big factor influencing soil structure development. And this happens over like hundreds of years. And so it takes time for structure to develop. On the left-hand side, you see a really heavy clay soil that is shrinking and swelling. So in the photo, it is dried out, and so it has basically shrunk. And then when it gets wet again, it will swell up again, and that can affect soil property or the soil aggregate formation. So this is an extreme example, but you can have various amounts of clay that shrink and swell in the soil all the time. You can also be influenced by soil organisms, and then of course tillage practices can alter soil structure quite dramatically. This is just an example, again, a little bit older image, but I kind of like using it. It illustrates the soil structure of a high organic matter soil and a low organic matter soil before and after wetting. And you can see that the soil with low organic matter, which basically is organic matter is providing glues that help to hold together the soil into aggregates. So if you are missing organic matter, you can see that by wetting the soil basically just falls apart and dissolves and loses its structure. And so we would use properties like wet aggregate stability to measure how well the soil holds together. And that's a good indication, important because it influences water infiltration into the soil and also creates resistance to soil erosion. If we're looking at different soil properties, you might consider the natural soil on the left. Again, you have a nice granular structure at the soil surface and then some different angular, blocky, and so on structures in the subsoil. But if you take a closer look at the problematic soil, soils with problematic structures could start right at the soil surface. So you could have a surface pan or cap. Essentially, this would be crusting on the soil surface that is happening when you have low soil organic matter and perhaps low soil pH conditions or high sodium conditions. But the bottom line here is that you have this crust forming on the soil surface that could impede water penetration going in, but also seedlings from emerging. You might have massive conditions in the topsoil, especially if you have severely compacted soils. When you get a little bit deeper, you might have this cultivation pan where the shearing force of tillage equipment is creating this breakdown of soil structure and flattening it out and creating this layering or platy effect that will impede water movement. So let's take a look at a couple of examples of this. And so here's a nice soil again with very even root distribution. This is something you can go out in the field and take a look at. Are the roots distributed evenly throughout all of the soil? And can you see lots of pores in the soil and perhaps evidence of soil organisms moving in and through the soil? At the opposite extreme, you have this great big clump of soil. The gray condition actually is suggesting that there's a lack of oxygen, so anaerobic conditions. And and you can see that there's very little rooting that's going on through this soil. So this is an example of a very extremely poor soil structure in a massive condition. If you look at soil compaction, so that's that process of basically compressing the soil and breaking up the structure. You can result in good indicators of that are if you stick your shovel in the ground and you're getting these big blocks or chunks coming out of the soil. That's definitely a problematic condition. Other indicators of compaction, so this is the second photo from the left is a tillage pan, and you can see that the roots of the crop are going down and then they turn completely sideways so that they're hitting a plow pan and basically a compacted zone. Now that can cause perching of the water, so poor water infiltration, and as well as reducing the root distribution in the soil. Here's another example. In the middle, you have roots that are growing, focused on growing in a crack between larger soil clumps rather than being evenly distributed in the soil. That's another indication of soil compaction. As we move to the further to the right, you can see kind of a layering effect of compaction that's created this platy condition and some shearing action. So ultimately we have, these are some things that you can go and dig in your soil and look for and see if you have a compacted soil condition. This greatly limits rooting through the soil and also relieves low oxygen content in the soil. So take a shovel and just dig around and see what you see. But you can also perhaps buy or borrow a penetrometer. A penetrometer runs in the order of around about $400. And you simply push it into the ground and you can see on the little dial the amount of pressure that you're putting onto the probe. And essentially the higher the pressure, the more compaction you have in your soil. Of course, if you hit a stone or something like that, then that's problematic. So you have to do lots of poke the ground a lot, especially if you have a stony soil. And depending upon what kind of soil you're using, you would use different tips to more accurately represent the resistance of, in the soil. So a penetrometer you could probably borrow from from your extension department in the government, or from a local soil testing lab, or perhaps a university soils department. Another thing that you can do to measure soil structure or interpret it is look at infiltration of water into the soil. So here's an example of a very simple thing that you can do. Essentially get a ring a metal ring is preferred, just so that, because you have to hammer it into the ground an inch or two. And then you lay a piece of saran wrap or plastic into the core, and you pour in a known amount of water. So why do you put the plastic in? That's so that if you're in a cultivated soil condition, you're not disrupting the soil structure, which could slow the water infiltration. And you can just and when you pull the plastic out, then the water starts going down all at once, and you're not disturbing the soil by the pouring action. But it also allows you to have your stopwatch ready, and when you pull the plastic out, you can start your stopwatch, and you can measure how much time it takes for the water to infiltrate into the soil. And so if you're always using the same core size or cylinder size and the same amount of water, you could do relative comparisons in your field. And so there are some more standard approaches to this. You can look at the videos that I've shown here and look at infiltration into the soil. Infiltration measures the water infiltrating into the soil surface. Percolation measures water movement through the soil. And so if you repeat this exercise after the infiltration test, leave the core in place and do it again, you'll measure percolation of water through the soil in a saturated condition. So how might we alleviate soil compaction? Well, you could go to a broad fork if you're working with small soil beds. In larger, in all scales, you can use biological materials such as tillage radish, which will grow its root into cracks in compacted soils, and then as it grows and expands, it'll swell and break up soil compaction. You can also go to subsoiling of your soils, and you can go from a single shank subsoiler, which I'm using here on my little 23 horsepower garden tractor. We'd sink that in the order of 20 inches or so deep to break up hard pans. Or you could get heavier equipment. And when you're subsoiling, you don't want to mix your topsoil into your subsoil. You're basically just trying to fracture the hard pans down below. So there's different types of subsoiling equipment and shanks that you can get with slightly different effects depending upon your soil type and what you're looking for. So now let's talk about poorly drained soils. And poorly drained soils can significantly restrict your rooting volume and your root growth. So if you have a perched water table and the soils are saturated, most plants are not adapted to that, and so they will not root into those saturated conditions where there's oxygen deprivation. A lot of plants can tolerate that for varying periods of time. Some can tolerate it for even a few weeks. Some are less tolerant and will only tolerate saturated conditions for a few days. But these saturated conditions also will suffocate soil organisms. And so ultimately, if you want to have a good soil health condition, you need to ensure that you have good soil drainage. And one of the ways that you can find out if your soil is well drained or not, if you're buying new land or if you're just exploring your own soils, is dig a hole in the ground, and if you see this kind of splotchiness of a red and gray colors, that means that when it's a gray, like a really gray color, it usually is an indication of anaerobic conditions, and poor drainage, so saturated soils. And if you have a splotchiness of red and gray, then you might have varying periods of saturated conditions. So that might happen in the springtime, then it might dry out, but you might also then have saturated conditions again with after heavy rainfall events. So dig in the soil, see if you see this splotchiness, and also a good indicator of really poorly drained conditions is a kind of a septic-y smell in the soil. So obviously in the spring or even in the summer, if you dig a hole in the ground a foot or two deep and you're seeing water accumulate in your hole over time, then there's a good chance that you have poor drainage. So how do we deal with poor drainage? Well, we can create ditches in our fields and have raised beds or crowning the land so that it's so that water runs off and into ditches that would carry the water away. That takes a fair bit of land shaping. So if you're dealing with smaller land areas, that might be more feasible, just having a blade on the back of your tractor. You can do this at a larger scale. Obviously, we see this on our dike lands, but there's a lot more soil movement happening there. Otherwise, you're probably looking at putting in a tile drain system, and there are operators, not too many of them in our region, but they do have big machinery that will go out with laser guidance and do a really good job of putting tile drain in at controlled depth and making sure that you're getting proper drainage condition. But you can also, if you have a smaller land area, you could rent a mini backhoe like I did here, and you can trench the soil yourself. And I used the mini backhoe to create the trench, and then I backfilled with my own tractor. You can see that there's two different colors of tile here in the two photos. The black one is just pure plastic Big O pipe. The white one here is the same, the Big O pipe, but it has a silt sleeve on it. So basically it's keeping the silt from getting into the pipe and clogging it up. It costs a little bit more money, but if you want to ensure that the drainage tile doesn't get clogged with soil through its holes, then you might consider doing that. So soil drainage is something you can do yourself. You do need to be very conscious of how you orient your tile drains and the spacing. So if you have a fine textured soil, then you would space your tile drains closer together. If you have coarser textured soil, you might spread them further apart. And the deeper you put your tile, the more it'll draw the water table down. But again, it depends on the spacing, the distance that you have these tiles apart. So my tile drains I put in at around 22 to 24 inches deep where I could. I did end up, you have to be careful if you're planning on subsoiling your fields. You got to make sure that your tile drain is below the depth of subsoiling, or be conscious when you're subsoiling not to hit your tile drains. Yeah. Great, so we've talked a little bit about soil structure, some basic soil physical properties. Now we're going to talk about some basic soil chemical properties. And soil pH is another big one. It's kind of a standard thing that you'll see on every soil test is the soil pH. And so soil pH is a measure of the hydrogen ion concentration in the soil. And it's measured as the negative log of the hydrogen concentration. So what does that mean? Because some people get mixed up. Usually lower number in soil pH means that you have a more acidic concentration or acidic condition, which actually means higher concentration of hydrogen. So let's just look at the math here. So if we're looking at, from a chemistry perspective, and a concentration, 0.1 moles per liter of hydrogen is essentially 10 to the minus 1 if we're going this log or negative log scale. And when you use the negative log of the hydrogen ion concentration, you basically just are counting how many decimal places you're moving backwards below 0. So in the 10 to the minus 1, we're only moving 1 decimal place back, and we actually have a pH of 1. So that would be a high concentration of hydrogen and a very, very acidic condition, which would not be natural in most cases. When we have 0.001 and you count how many decimal places are moved back, and it's 10 to the minus 3, and you have a pH of 3. Similarly, if you have 0.0000001, you have 10 to the minus 7, and so the concentration of hydrogen is going down. It's becoming smaller and smaller, and the pH is 7, and that's what we regard as a neutral soil pH. So lower pH means higher hydrogen concentration and a more acidic condition. And hydrogen is a fairly aggressive cation, and it can bump other nutrients out of the soil. And so that's one of the reasons why it's a bit of a concern if it's too acidic. Higher hydrogen concentration creates an acidic or sour condition. It can corrode metals and also create significant nutrient imbalances. So acidic soils are more common in our area and something that we need to manage. So if we look at the soil pH ranges here, you can see that you'll normally see recommendations that we want to have. The optimum soil pH range is in that 6 to 7 range typically. And as we go to below pH of 6 and especially below pH of 5.5, then you start to have more issues with lower nutrient availability, and perhaps even as you get lower in your pH, you could have aluminum toxicity issues. As you decline in soil pH, you're also having lower availability of phosphorus, calcium, and magnesium. You can have the opposite issue with really high pH soils, and that would be more common in prairie regions, so dry soil conditions, where you can also end up with deficiencies or imbalances, I should say, of various nutrients. So deficiencies in iron and phosphorus and zinc, but also perhaps imbalances of calcium, magnesium, and potassium. One other issue with soil pH is that soil, as we're very familiar with in organic systems, we want to fix nitrogen using legumes, and we need rhizobium bacteria to do that in most cases. And rhizobium bacteria tend to prefer a more neutral soil pH, so in that 6 to 7 range. And so if we have really acidic soils, we are likely to have less soil nitrogen fixation by the legumes, just because the bacteria aren't as tolerant to that low pH condition. So you can see the nodules here, and they basically are optimized in the mid 6.5 range, and then decline beyond that. So, so soil pH is a very important property that influences nutrient availability just from a chemistry perspective, but it can also influence soil biology. And different plants are also adapted to different soil pH conditions. This is an example of a recently plowed old hayfield, and I took this photo just to illustrate. Well, what happened was the farmer had plowed the land and flipped the topsoil that was there and brought the subsoil up to the surface. And it was an old hayfield, and it also has fairly poor drainage. But on the right-hand side of the screen, you can see very poor plant growth, and that's relating to various nutrient deficiency issues. On the left-hand side, it's the same soil and same processes, but the farmer had spread, kind of in strips as a test, some fish waste and shell material from, I believe, lobster and crabs and so on. So when you look a little bit closer, you can see soil phosphorus deficiency issues, multiple nutrient deficiency issues, and that's from inverting the soil. And certainly that acidic soil pH condition was a big factor in influencing this, but also probably lower background soil fertility conditions. There also was issues with wireworm damage in the crop because it was just coming out of sod, but that's another issue. So in terms of managing soil pH, we need to think about liming it to correct the soil pH and bring the soil from acidic conditions to a little bit more neutral. And again, this depends on what kind of crop you're growing, but most of our crops tend to prefer a little bit more neutral soil pH. And potatoes are a bit of an exception. They tolerate more acidic soil conditions, and if you want to avoid scab on your potatoes, then you want low pH because the scab itself can't tolerate the low soil pH. If we're trying to bring a soil pH up, there's different limestone materials that we can use, so calcitic limestone or dolomitic limestone. The difference between them is essentially that calcitic limestone only contains calcium carbonates. Dolomitic limestone includes some magnesium in it as well as the calcium. And so depending upon your soil test, you should check out your soil test report and look at the calcium to magnesium balance on your soil test report. And so you would look under base saturation, and if the ratio of calcium to magnesium is too high or too low, then that will determine which limestone you should be using. So your ideal range is around 5:1 or to 8:1 for calcium to magnesium. Otherwise, you can create imbalances in different nutrients. Magnesium, by the way, if you have excess magnesium, it can also displace potassium and make it harder for the plant to use potassium. So the moral of the story here is don't just randomly select which limestone you're going to use. Make sure that you are considering whether you need magnesium or not. If you don't need magnesium, if you have lots of magnesium in the soil, then use a calcitic limestone. You can also look at using wood ash, which is perhaps more economical. Wood ash characteristics can vary depending upon the source of the wood ash, but many of them, aside from having a liming potential, they can also provide nutrients such as calcium, potassium, and magnesium as well. Okay, another thing that you will see on a soil test report is cation exchange capacity. And cation exchange capacity is a measure of the soil's ability to hold on to cations, which are positively charged molecules. So down at the bottom of the screen, you can see a list of some of the cations that the soil might contain. So ammonium, calcium, magnesium, potassium, iron, they are all valuable nutrients that our crops use. Hydrogen and aluminum tend to, especially aluminum can be a problem, and hydrogen is okay if it's at the right balance, like the right pH range. But if it's in excess, it can actually displace some of the other cations, which we'll talk about shortly. Meanwhile, anions include the list below that you can see. I won't go through them all. So why is this important? Well, it ends up that clay colloids and humus, so organic matter in the soil, have a negative charge around them. So you can see this particle and it has a whole bunch of negative signs around it. And if you have, just like when you have a magnet, a negative charged soil material will attract positively charged ions or molecules. So the more negative charge we have, the more cations or ammonium, calcium, magnesium, and potassium the soil can hold, which is really valuable because it can enhance your soil fertility. So let's take a look at that a little bit more closely. So here we have the clay material in the center and all the negative charges on the edges of the clay. And you can see all of the cations in this dark blue area around the soil particle. And those nutrients aren't attached to the soil particles. They are what we call adsorbed. And so they are exchangeable with the lighter blue area, which is the soil solution around the clay particles. So depending upon what's in the soil solution, the cations out here could exchange with the cations that are attracted more closely to the soil particles. So the capacity of the soil to hold these cations is really important, because if these cations aren't being held onto by the soil and attracted, then if they're in soil solution, they will go wherever water goes, and if water is being leached out of the soil, then you'll basically lose those nutrients. That's a big problem, especially in tropical regions where you have so much precipitation. Almost any nutrients that remain in the soil are getting washed out, and so almost all the nutrients are being held by mostly vegetation. So you can see, meanwhile, the negatively charged ions, the anions, are all out in the soil solution, and they would be very mobile and moving wherever solution would go. So if you have a high cation exchange capacity, you have a high ability to hold cations. Now if you have, and these are exchanging. Now if you have excess hydrogen in the soil, so a really acidic soil pH, you can see the hydrogen can go in and bump the calcium out of the exchange and into solution. And when it's in solution, then it's vulnerable to being lost or leached away. And that's not very desirable. So that's one of the issues of having a really acidic soil condition, aside from other ways that nutrients are being immobilized. So that's cation exchange capacity. So the other thing that you'll see on your soil test report is something called base saturation. And this is, so when we talk about cation exchange capacity, different soils have different abilities or volumes of cations that can be held. And the base saturation represents the percentage of the cation exchange that can be held by base cations, and mainly we're interested in calcium, magnesium, and potassium. The acid cations would be hydrogen and aluminum. So in other words, these three nutrients, calcium, magnesium, and potassium, are really desirable to have, but hydrogen and aluminum are not very desirable, and so and can be problematic. So we want most of our cation exchange to be occupied by these three nutrients. And so when you're looking at base saturation, you're looking at for higher concentrations of calcium, magnesium, and potassium. And of course, as I mentioned previously, you're looking for the right balance between these three nutrients as well. So if you have excesses or deficiencies in nutrient supply, you could look at the base saturation. So what do our soils have in terms of cation exchange capacity? So our really sandy soils could have cation exchange capacities of 6, as low as 6 per milliequivalents per 100 grams. Loamy soils would be 6 to 12 milliequivalents per 100 grams. And when you get into finer textured soils, you could get into 15 to 25 milliequivalents per 100 grams. So how do you change cation exchange capacity? It's very closely linked to soil texture. So the more clay you have, the higher your cation exchange capacity. So the only other factor that influences it really is organic matter content. And so if you increase your soil organic matter content, you can actually increase your cation exchange capacity in the soil and your ability to hold the nutrients. There's also, more recently, people have started to use biochar, and biochar can also enhance your cation exchange capacity in the soil. And that would be another discussion for another day relating to biochar. So be careful and do a lot of homework before you start using biochar. So we've gone through a lot of the fundamental soil properties in terms of physical and chemical characteristics, and we have talked about how we might manipulate a lot of those basic soil properties in our land management to improve soil health and function. We haven't gotten into biological characteristics yet for the most part, and that will be part of our next presentation. So I hope you enjoyed that, and it's a reminder that go back and take a look at some of those fundamental properties. And if you want to create that healthy rooting environment with healthy soil biology, you have to start by having healthy soil structure and also healthy soil fertility and basically soil pH conditions. So next we'll be talking more about balancing your soil fertility and using soil biological activities and so on to address that. If you have deficiencies in your soil, you need to correct them, and so there's some of those basic soil properties that you have there. And we'll talk more about using green manures and organic amendments in our next presentation. Before you start farming your some new land, if you're just buying new land, be careful in terms of what kind of land you're buying to ensure that it's suitable for the kinds of crops that you want to grow. And so there's lots of properties that you can look at that we've talked about, but also consider your climate, irrigation availability, how you might keep pests out, and make sure that your crop selections are suitable for the site so that you're not fighting with your soil all the time. So being conscious of your soils and doing good site preparation, improving your soil structure and drainage, and getting some background soil fertility will take you a long ways in having a successful operation. So I've got lots of different resources that are available here, and so you can pause the video and take a look at this list, and we'll also make them available online. So hopefully that was of interest to you. We invite you to visit the Organic Agriculture Centre of Canada website at www.dal.ca/OACC. We also have a free newsletter that you can sign up for on our site, and you can follow us on Twitter at Organic Ag Canada. Thank you for listening.